but today we'll try to cover it in more depth. So yes, one is the shape, right? So if you can refer this particular diagram, and for any of this figure, let's say if your data is divided into such scenario, let's say let's just focus on the first cell, right, where we have two circles. So easily we can our eye can detect that there are two clusters, one inner cluster which is highlighted by this orange line, or you can say the orange color, and the outer circle which is highlighted by this blue color, right? So that is for this first figure. Similarly, you can try it with the other figures too. But whenever this kind of shapes are there, it is very difficult, or you can say it is almost impossible to classify such shape, or you can say the non-convex function, whenever we are dealing with the partitioning based method like k-means or k-medoid, right? Another limitation is that algorithm are, you can say, highly diverted towards this outliers or the noise. So if you have two or three noise or two or three outliers, they can change the mean value as well as middle value, and that we don't want to change it for one, two or five examples, right? Where 100 example belongs to some cluster, while one, two or five example which are the outlier may belongs to very far from the cluster. But if we try to include that outlier within the cluster, what happens? Your mean value is going to change, and ultimately your cluster size or shape is going to change, or it outlier can affect the performance, right? So to overcome these two issues, we are trying or we are learning some new technique, and in that direction, the first approach that we have started in the last lecture is this density based clustering algorithm, right? And in this density based clustering algorithm, in the last lecture we have seen some definitions. We haven't discussed actual algorithm, that is dbscan, that we are supposed to discuss today. But today we'll first revise this terminology, because that term, core point, the boundary point, outlier point, as well as the cluster, and that all terms are very important to understand the algorithm. That's if you understand the algorithm. See, one good benefit of this clustering is, if you just know exactly what happening inside that particular algorithm, then compared to the other categories, or you can say compared to the supervised learning, implementation as well as understanding of this clusterings are very easy, right? You just need to focus on how that particular algorithm works. That's it. Mostly no mathematical equation, no statistics calculation, no probability, right? So these are some you can say benefit of this clustering. Those who had maths, they can think in that direction, right? But always try to think about the real world data whenever you have some data. So nobody is going to tell you that whether you are supposed to apply supervised learning or whether you are supposed to apply unsupervised learning, go for the clustering, go for the k-mean, go for the linear regression, and so on. So nobody is going to tell you that. You have to analyze the data, and based on the data that you have, or whether you can have some more data, or maybe whether you can add some more features to that data, whether you have the label, and likewise based on that description you are supposed to decide which algorithm will best suitable for this kind of data, right? And accordingly you have to choose the algorithm, right? Whether you can use, whether you should go for the classification, or you should go for the regression, or let's say you should go for this unsupervised manner or some other techniques, right? We'll also introduce ensemble learning, which is actually the combination, right? So there are many ways to solve particular problem, but which approach should be best suitable depend on the data, and you are supposed to identify which should be the approach. Fine. So with this, let's go back to the next slide, where we are starting the discussion of this density based algorithm. And right, and if you can recall the last lecture, we have discussed this features. It can handle the noise, and with the one scan itself you are supposed to identify, or you are supposed to find the clusters, right? And using some density parameter, or you can say depth parameter, or in another term you can say number of points within the cluster. Using that parameter, you can identify what should be the termination condition of this density based algorithm. And Remember that the previous algorithm, partitioning based algorithm, that are independent to number of examples belongs to a particular cluster. Right? There is no relationship between how dense your cluster is or how sparse your cluster is. The previous algorithm, that is partitioning method, just focus on, you can say, distance, right? That's, you can say, distance based learning, while this category is density based. So we are always focused, whichever algorithm you consider. This dbscan is the one algorithm which is in our syllabus, so we'll discuss that, but there are many other density based algorithm. But one common feature of this density based approach is always we are concerned about how many samples, or you can say how many examples are there in particular cluster, right? So with this basic understanding, and we have started the discussion of this db scan. For that, we have discussed these two parameter, epsilon, that is eps, and minimum number of points, that is mean points, right? EPS or mean points, that are the two important feature, or you can say that are the two important uh, input that you are supposed to give to your particular algorithm, which will decide the performance, overall the performance. So these two are the hyperparameters, epsilon, or you can say the EPS, and mean points. And where we know that the EPS is just the radius. So whenever you consider any point from your full data set, whenever you pick any point, for that point, you need to consider the radius of size e. Right? The unit can be any, depends on the data. So let's say if I say the radius is 1 meter. Let's assume that your data is distributed in very large space, and let's assume the radius is 1 meter. So from a particular point, you need to consider the 1 meter radius, and in that 1 meter radius, how many points are there, that will decide whether the current selected point is a part of cluster or not, right? And so on. And the second parameter is minimum points. So that is, whenever you say that, let's say the radius is 1 meter, then from particular point within the 1 meter radius, how many points are there, that count plus the current point which you have selected right now, right? So the total number of points which are over there in the particular given EPS radius, that you can say n EPS of particular point P, right? And if it is higher than this mean points, then the selected point is eligible to be a core point, right? If you can recall the last lecture, we have divided the points into three categories. Can anyone just recall the three categories? Right, the border, outsider, or the outlier, and the third is the core point. Fine. So in this DB-scan algorithm, what we'll do, we'll pick all the points one by one, and we will verify whether that particular point is core point. If not, whether it's in boundary point. If it's not a boundary point also, then we will label it as an outlier, or you can say the noise point. Fine. But to decide this all parameter, whether it's a core point or it's a boundary point or it's an outlier, we will use these two features or two parameter. One is EPS and minimum points, right? So before revisiting this directly density reachable concept, or you can say before revisiting this definition, just focus on this given figure. And let's say this point is Q, right? My minimum number of point, or this hyperparameter value is 5, and the EPS value is 1 centimeter. So By keeping this Q as the center, we will draw a circle with the radius 1 centimeter. And now we will count how many points belongs to that particular circle. Fine. So for Q, can you tell me what will be this NEPS value? For this particular point Q, can you identify what will be the NEPS value? What about P? This is the point P, and this upper circle is of P. So what will be the NEPS of this P? So this 1, 2, 3, 4, and remember that we'll also consider, yes, for NEPS it's 4, but whenever we consider the concept of core points, we'll also consider this given point P in the calculation. Fine. So the NEPS you can say 4, while the total neighborhood points are, you can say, 5. Right. So now let's look at this definition once again. Directly density reachable. A point P is directly density reachable from Q if it is satisfied, if it going to satisfy these two conditions. The first condition, P must belongs to this NEPS set of Q, right? And the second is the Q that we are selecting, it must be a core point. So one important observation over here is this directly density reachable concept is applicable to core points only. Fine. And if we just simplify this definition rather than writing it into this complex form, simply whenever you consider any point, if it is a core point, then in the boundary, or you can say in the neighborhood of that core point, whichever other points are there, that you can say directly density reachable from a selected point. Is it fine? So if I make it more simple, you need to just consider one point, draw a radius of given EPS size, and within that EPS size, whichever points are there that are directly reachable from the current point, if current point is core point. And if it is not a core point, then you cannot apply this directly density reachable concept. Right? Then we have some other definition, so we'll see that. Fine. Okay. Next, density reachable. The first concept was directly density reachable. Now the second is density reachable. So you can say point P is density reachable from Q if you have this chain P1, P2 up to Pn, where in a chain the first point P1 is Q The last point Pn is P itself, and in between you have some other points, maybe let's say P1, P2, P3 or so on. But this last line is very important, such that P of I plus 1 is directly density reachable from Pi. So I'm giving you some time, just read this definition once again, and let's assume n is equals to 10, right? So just reread the definition and try to answer the question. The question is, let's assume that n is equals to 10. So can you tell me, whenever I want to apply this concept, then minimum how many core points are needed? Okay, so the question is, assume that in the chain, let's say P1, P2, P3 up to Pn, we have 10 points, right? And such that the first point is your Q and the last point, 10th point is P. So in out of the 10 points, can you tell me minimum how many points must be a core point? Then and only then I can say that it's in density reachable. The Q is density reachable to P. So we have to answer 8 and 9. 8. Okay, so one hint, just read the second statement, and I guess now the answer will be clear. Except last, all other must be a core point. Means we need total 9 core points minimum. It's fine if the last is not a core point. That is, if it's fine if P is not a core point, but starting from Q up to P1, P2, P3, up to whichever intermediate points are there, they all must be a core points. Why? Due to this last line, which say that directly density reachable from Pi. P of I plus 1 must be a directly density reachable. And we know that when directly density reachable is applied, whenever it's a core point. Is it clear or any confusion is there in this definition, density reachable? So this one relaxed criteria compared to this directly density reachable. Right? Density reachable is relaxed criteria compared to the previous point. Yes, not only P1, starting from Q, P1, P2, P3 up to all others, except the last point that is P. Because the last line is applicable to all points in the chain. So if you observe P of I plus 1 is directly density reachable from P of I. Right? It is not the case that it should be applicable to the initial or the last point, right? So in a chain, whichever points are there, to all it is applicable. So now observe this first figure and just observe the circles of this Q, P1 and P. Right? And we are trying to identify whether this point Q is direct density reachable to P or not. Let me just repeat the question. What we are trying to identify, this P Is density reachable from Q or not? That's our aim, right? So what's your answer? Yes or no? Okay, so Muktan's question, for P to be directly density reachable to Q, both needs to be a core point. Yes or no? So anyone wants to answer this? Priyal said no, one must be a core point. Or rather than one, can we say specifically P must be a core point? Source should be a core point, and your destination, in general, we can say the source should be a core point, and the destination for which we are checking, that may or may not be a core point. So it is relaxed criteria for the destination. So whenever I say Q is directly density reachable from P, in that scenario, P must be a core point. Right, Mayank, correct. Fine. So there is no comment on the Q. It may be a core point or it may not be a core point. Fine. So we are not checking whether the Q is core point or not. Fine. So that was the directly density reachable. Next is the density reachable. So now what we are doing, it might possible that, or let's make it more, very simplest version. Let's consider this circle as a range, and the point from where, or you can say the source, is the center. Fine. So from the center, if it's in a given range or in a given radius, if you have whichever points are there in a given range or given radius, that all are directly density reachable. If in the range we have some minimum number of points, that are the points, the number of points should be higher than or equals to mean points. Just consider this simplest diagram. This T-shaped point, assume that it's in center, or you can say that is the point for which we are checking whether it's in whether other points are density reachable or not. Fine. So let's say this is point P1, this is P2, and the last is this P3. Assume that this P1, P2, P3 are in the given range of E, right? It's in the range of epsilon. And further assume that mean points is 2. So now what's your comment about P1, P2 and P3? Are they directly density reachable from T or not? Yes. Fine. And now let me just redefine the criteria. This P1, P2, P3 all are in the range of T. Mean point is equals to 4. And now can you tell me whether this P1, P2, P3 are you can say directly density reachable from T or not? The answer is no. Reason, mean points is 4. So if mean point is not 4, sorry, the number of points are lesser than 4, this T itself is not a core point. So no matter whether this P1, P2, P3 are in the boundary of T or they are outside the boundary of T, but uh, we cannot say that it's directly density reachable. Why? Because T itself is not a core point. Fine. So these two conditions are must be hold. The first condition is T must be a core point. The second condition, these points must be in the territory of this T, within the territory of this T. હજુ પણ કન્ફ્યુઝન હોય તો સિમ્પલ ટર્મમાં કોઈ બી એક પોઈન્ટ ઉપાડો, એની બાઉન્ડ્રી લો, જેટલી બી બાઉન્ડ્રી કીધી હોય, લેટ્સ સે બાઉન્ડ્રી કેટલી કીધી હશે, EPS જેટલી, એપ્સિલોન જેટલી, રાઈટ? એ બાઉન્ડ્રીની અંદર જેટલા પોઈન્ટ હોય એ કાઉન્ટ કરો, રાઈટ? જો એ મીન પોઈન્ટ વેલ્યુ જે આપેલી હોય એના કરતાં વધારે હોય, then all that points are directly density reachable. બાઉન્ડ્રી બહારના તો આમ બી નથી જ, રાઈટ? આપણે ખાલી બાઉન્ડ્રીની અંદરના જે જેટલા છે એની જ વાર્તા કરવાની છે. બાઉન્ડ્રી બહારના આમ બી ડિરેક્ટલી ડેન્સિટી રીચેબલ છે જ નહીં. સો બાઉન્ડ્રીની અંદરના બધા પોઈન્ટ્સનો સરવાળો કરો, જેટલા બી થતા હોય એટલા. ઇફ ઇટ ઇઝ ગ્રેટર દેન ઓર ઇક્વલ્સ ટુ મીન પોઈન્ટ્સ, એ બધા પોઈન્ટ્સનો સરવાળો એના કરતાં વધારે અથવા એને સરખો થાય, then you can say it's indirectly density reachable. Fine? Whichever points are within the boundary. પણ જો એ સરવાળો મીન પોઈન્ટ્સ કરતાં ઓછો થાય, then we will say they are not directly density reachable from the center point. Why? Because center point itself is not a core point. Fine? Easy? Directly density reachable. Next, one relaxed criteria is density reachable. So it's fine in the density reachable, what the scenario is, it's fine if the particular point is not in the range of my territory. And my territory means a particular point which is a core point. So if a particular point is not in the range of a core point, but there is some third point, or there should be some intermediate point which is in the range of current point, and that intermediate point is also a core point, that means in its boundary there should be some other points. So that other points which is not in my boundary, but that other point belongs to the boundary of intermediate point, and that intermediate point is also a core point, then I can say whichever other points that are in the boundary of that second point, that all are density reachable from a current point. Fine. So with this understanding, let's revisit this example. So here we have three circles, 3 points, Q, P1 and P. Right? Let me just highlight that point so the thing might be more clear. This is P, this is Q. Right? These green highlighted points are Q, P1 and P. Right? And now we are considering, I hope you can identify which is the circle of which point. Right? Which should be the circle of Q, which should be the circle of P1, and which should be the circle of P. Now, just consider a point Q. For point Q, what's your comment about P1 and P? related to this directly density reachable, whether P1 is directly density reachable, yes or no, P is directly density reachable, yes or no, with respect to Q. Yes, mean points 1, 2, 3, 4, 4. And EPS is given, right? The boundary is given. Fine. So from with respect to Q, P1 we can say is directly density reachable. Why? Just focus on the circle of Q. Right? Just focus on this circle. Within this circle, first of all, within this boundary, calculate how many points are there. If number of points are higher than or equals to 4, then we can say Q is a core point, and then we can start this all stories, right? The directly density reachable and density reachable and that all, right? If it is not a core point, don't worry about all this story, right? None of these concepts are applicable. And ultimately, these core points are very important in this DB scan algorithm, right? They are actually useful to decide the cluster. So now just pick the point Q and just consider the circle of Q. In the circle, calculate how many points are there, whether they are higher than or equals to 4. So answer is yes. As the answer is yes, this Q is a core point. Fine. First condition satisfied. Second condition, whether in the boundary, do we have the points that we are discussing? That is, in the boundary of Q, do we have P1? Do we have P? So if you observe, Q is core point. So બીજું કંઈ વધારે વિચારવાની જરૂર નથી. Q is a core point. Now check the boundary. Within the boundary, if P1 is there, done. If P is there, done. But if you observe, P1 is within the boundary, but P is outside the boundary. Fine. So as P1 is within the boundary, Q is a core point. As these two conditions satisfied, we can say P1 is directly density reachable from Q. Right? But we cannot say the same thing for P. Why? Because if any one of these criteria is not satisfied, you can simply say that it's not directly density reachable. So in the case of P, which criteria is not satisfied? P is not in the territory of this Q. Right? It is not within the boundary of Q. Fine. So comment, or you can say our analysis so far is this point P1 is directly density reachable from Q, but we cannot say same thing for P, right? So now we have second definition, that is density reachable. Directly નહીં તો કાંઈ નહીં, ચલો વાયા વાયા જવાય છે. Then we can say it's in density reachable. So in this definition, what we need to do, first of all, right now we are checking about Q and P. આપણને એટલી તો ખબર પડી કે Q and P is not directly density reachable from Q. So next, let's check whether P is density reachable from Q or not. So for that, what you need to do, you need to consider, you need to identify some chain, right? એક કરતા વધારે પણ હોઈ શકે. There might be multiple chain, but you need to find at least one chain such that Q થી P વચ્ચે કંઈક path establish થતો હોય. So right now, if you consider the given chain, that is Q to P1 and P1 to P, in that path, whichever points are there, except P, whichever points are there, all must be a core point, and point P is in a territory of some last point, then we can say it's directly density, it's density reachable from Q. Fine. So now with this, now read the definition once again. I hope now once you read the definition, then it will be definitely clear, right? So we have some chain P1 to Pn, where P1 is the first point, that is Q itself. Pn is the last point for which we are checking, which is P in the current example. But the requirement is P of I plus 1 is directly density reachable from Pi. That is, except the last point, that is, except point P, all other must be a core point. Q, P1, right now we just have two entity, right? Q and P1. So now just for this example, can you imagine whether this P is density reachable from Q or not? Answer is yes, P is density reachable from Q. Right? The path which is shown over here, it might not be clear that this Q P1 to P, from if you just consider that particular path, you cannot say that's density reachable. But just imagine some point, let's say in the boundary of this Q, let's just focus on this point P1. Right now in the territory of P1, let's just focus all the, as P1 is a core point, let's just focus some other point, let's say this point. Fine. Now, if you redraw the circle for this particular point, let's say this new point is P2. So if you redraw the circle for this P2, can I say that the P will be in the circle of that P2? And also, if you observe this dense points, we can easily satisfy both the condition, mean points condition, right? For this P2 also. Fine. So via that path, I can say that Q P1 P2 up to P, this P is density reachable from Q. Right? If you have mathematical tools, then I guess it's very easy to identify that circle and that all. But right now with the imagination also, I guess you can draw that circle, and you can able to detect that this Q is P is density reachable from Q. And why we are doing all this practice? To identify how dense the particular cluster is, or you can say to identify whether should I pick that point within the cluster, or should I just treat it as an outlier. And so that's why we are introducing this term. Directly density reachable will definitely include. Density reachable will also include. Next, we'll see the boundary points that will also be a part of cluster. But if none of these criteria is satisfied for a particular point, then we will say that particular point is outlier and it doesn't belong to any of the cluster that we have identified with this technique. Right now, the last level, density connected, which is, you can say, one more relaxed criteria. So just observe, uh, right now we are talking about point P and Q once again, right? So if let's say P and Q, if you just observe this figure, P and Q are definitely not directly density reachable. They are also not the density reachable. But here there is one point O such that P and Q are density reachable from O. This is density reachable, right? This is not density, not the direct density reachable. So if you observe this point O, with respect to O, this P as well as Q both are density reachable. Then you can say that P and Q are density connected. So once again, you need to form one cycle. Let's assume similar to the previous example, there might be a confusion. What is the difference between this density connected and density reachable? So to answer, if I just ask one question and if you're able to answer that particular question, I guess it would be clear what should be the difference. So the question is similar to the previous example. Let's say we have 10 points in the chain starting from P up to the Q, P, P1, P2, P3, and somewhere we have point O as well as at the end we'll reach towards the Q. And so there are 10 such points. So can you tell me out of the 10 points, minimum how many core points must be there to satisfy this density connected? Minimum. The one answer that 3 or 2. 3, 2 or 3 plus 2 or 3 into 2. Mayank? 2. So Mayank said 2. That are both the boundary points. Then what about the second line? If you just read the second line, both P and Q are density reachable from O. And whenever we say from O, something should be reachable. So O must be a core point. Priyal says 8. So which 2 you have excluded, Priyal? P and Q. Right, correct. So the only difference between this density reachable and the density connected is, in the case of density reachable, minimum number of core points needed are 9, starting from Q up to all other except P. Whether P is core or not, it doesn't matter. Similarly over here, in a chain, except both the boundary point, that is except P and Q, all other point must be a core point. Whether P and Q are core points or not, it doesn't matter. Fine. So I hope now it's clear what exactly the difference between directly density reachable, and density connected. And so over here, the minimum number of points needed are minimum core point should be 8. Density reachable, minimum core point should be 9 in the case of 10 examples. Right? So we have already introduced this core point, but let's see the formal definition. The core point is a point if it has more than minimum PTS value within its boundary or within its epsilon region. And so we already know this definition, so no need to re-explore the same definition again, right? And if you just see the example, the core point, if you see this min points criteria is 5. So if you observe this particular point and if you check its boundary, there are 5 points, right? So it's in core point. Yes, as we are drawing this circle boundary, it should be a center if it is 2D space. Right? 3D space, then we'll have that, uh, uh, you can say 3D, in a 3D space, we'll plot that. And when once we have the higher dimension, once again, we'll plot it in higher dimension, and the point must be in the center. Right? Because this EPS is the radius. So by keeping that core point as a center, we will draw a circle boundary with the radius is equals to 1 centimeter. Right? Then next definition, border point. So the interesting thing over here is border point is a point with fewer than mean points number of points. But It is in the neighborhood of a core point. Right? So now if you just refer this outlier point as well as the border point, that the circles are not exactly the center, but yes, practically it must be in the center, right? So if you just check this outlier point as well as the border point, and if you observe, none of them satisfy this mean point criteria. If you consider the border point, the count is just one, or if you consider this point, then the count is two, and the maximum count is two, but still it is less than five. If you consider this outlier, the count is zero. Once again, it's in less than five. So for outlier as well as for the border point, no, none of them will satisfy this mean points criteria. But the difference is, if you consider all the neighbor of this border, at least one neighbor of the border point is, you can say, a core point. And in this case of this border point, if you observe, that neighbor is this point, જે આપણે ભૂસી નાખ્યો. And thanks to this particular point, this current selected point, let me name it as P1, and let's just give this particular point named as P2. So you can say, thanks to P2, this P1 becomes a border point. Otherwise, there is a probability that P1 will be an outlier. Right. I will definitely repeat this. But before that, can anyone tell me whether this particular point is a core point or not? Try to imagine that circle. It's fine if you cannot imagine the exact 1 centimeter boundary, but approximately, right? Yes, so it's in core point, right? The name which we have given to this point is P2. Fine. So P2 is a core point. Now, just tell me whether this P1, is it a core point? For the P1, the circle is given, right? So P1 is not a core point at all. Fine. So if particular point is not a core point, and let's say this point is P3. What about P3? Is it a core point? So Devang said P3 is twice not a core point. No, right? But I feel this P3 is a core point. If I am imagining that circle, I guess 5 points will be there. Though it's very hard to predict the exact boundary. Anyone else agree with me? This P3 is a core point. Okay, so let's take this 10. P3 is not a core point, fine. So it doesn't matter. It won't affect our performance. But actually, you can draw the exit boundary to get the correct or the exit answer. But right now, let's assume that the P3 periphery did not contain the 5 points. So let's assume that P3 is not a core point. So now if you consider point P1 and check the neighbor of P1. So which are the neighbors of P1? Which points are in the neighborhood of P1? So Priyal said this is the point P4. બટ આપણે એને થોડો બહાર ગણીએ પ્રિયલ કેમ કે બાઉન્ડ્રી થોડો દૂર છે. But exactly, if you consider, see, whenever you plot this, there are no such large circles, right? We just have exit plotting, right? So in the plotting, it's fine. But yes, so right now let's assume that P2 and P3 are the neighbors of P1. Out of all the neighbors of P1, can we have any single one or more, can any single, or you can say one or more neighbor, which is actually a core point? That means right now for the P1, the neighbors are P2 and P3. So out of this P2 and P3, do we have any of them as a core point? Yes, so P2. If it is, if any of your neighbor is the core point, you can say the particular point P1 is a border point, right? So to become a border point, you need to consider two criteria. One, it must not be a core point, right? કોઈ બી point જેને આપણે border point કહીએ, it must not be a core point. So if it is a core point, there is no need to label it as a border point. But if it is not a core point, and if you check its boundary, in your boundary, or you can say in your neighborhood, if you find any point which is a core point, then the particular point or your selected point is a core, it's a border point. Fine. And the third criteria, it's not a core point in the boundary, or you can say in the neighborhood, we cannot find any core point, then we can say that particular point is noise or the outlier point. Right. So the beauty of this algorithm is it will identify the cluster as well as it will identify the noise point. And so that's why if you observe the full form, in the full form, we have that the clustering application, that is it is going to find the clustering as well as with noise. Even if you have the noise, you can still classify, or you can say you can still find the clusters, and you can also label the noise. These all are the noise point. So with this all discussion, let's just see the algorithm. The algorithm is very simple. You need to consider all the points one by one. So arbitrarily select one point P. Next, retrieve all the points which are density reachable from P. Right? Check the word density reachable. It's not directly density reachable. Right? Via P થી B, P થી ગમે ત્યાં પહોંચાતું હોય, either directly, that is either direct density reachable, or by some intermediate point. So all such points will consider, and whichever points that you can find, and if P is a core point, that all points which are in the territory of P as well as its neighbor core point and its neighbor core point and so on, all such points are part of one single cluster. Right. But if P is a border point and no points are density reachable from P, then we'll just keep the P and we'll try to visit the next point, right? We'll not try to find, or we'll not try to form a cluster with considering P, right? And remember that whenever you consider this DB scan based cluster, or you can say density based cluster, we do not have, this is the cluster center. We do not have any such cluster centers like the K-mean algorithm, right? We just have the cluster, right? How we have detected the cluster might be due to some arbitrary point, may or may not be the central point. Because if you consider the initial slide, the first slide, we may have the cluster where there are no center, right? This cluster are not a simple cluster where we can always find the center. Let's say there are no such square or the circle like diagram where you can always find the center, right? It can be it can be of arbitrary shape, so there may or may not be a center. So there is no concept of center in the case of this DB scan or any density based algorithm. We are just focused on the cluster, with the help of which point, that is just the selection, right? But we'll never label this P. Let's say thanks to P, if we are able to detect the cluster, we'll never label this P as the center of the cluster, right? And we'll repeat this process till all the points are covered, right? Maybe covered means all the points are labeled. So if it belongs to particular cluster, we'll label that particular point as a cluster's part. If it do not belong to cluster, we'll visit that point, we'll find its territory, whether it is able to form new cluster or not. If not, then we'll label it as an outlier. And so another way to look at this algorithm is compute the neighborhood for each point and identify the core points. Right, so just detect the core points, join the neighborhood of core points into a cluster, right? So this second point is actually, you can say, the definition of, can you recall another wording to represent a particular definition? So if you just see the previous slide, over here, density reachable, we have used the term density reachable, right? But if you recall the density reachable definition, it is nothing but it just represents this second point. Fine. And for each non-core point, either it can be a border point. If it is a border point, once again we'll include it into the cluster, or it can be a noise point. So if it is not noise point, we'll not consider it as a part of a cluster and we'll label it as a noise. Fine. And remember, these two are not the different version, or you can say sorry, these two are the different version of same algorithm, right? It is not the continuation. The first slide says the same thing as the second slide, but the representation is different. Fine. So next, just focus on this example. If you have this kind of cluster and if you apply this DB scan algorithm, you can able to detect the core point, border point, and the noise point, and based on that you can identify the boundaries. Right. So one example is given over here. EPS is 10, minimum point is 4, and this green points are the core points, blue points are the boundary point, or you can say the border points, and remaining red points are the noise point. Right. And if you observe, all 1, 2, 3, 4, 5, 6 cluster are perfectly identified by this particular algorithm, no matter whatever is the shape. Fine. And this last slide, where this density based algorithm may not perform well whenever you have this kind of data. Density might be of different size, and if it is higher dimension data. So with this, let's conclude this density based algorithm. Next session we'll start the next category, that is grid based algorithm. Thank you.
Good afternoon, all. Before we start, just check of audio. I think it is noise free. Is it audible to you properly? Can you hear me? Okay. So this time, possibly, we will not have the issue that we had last time. Let us see what we see today. Today, you will be clear of all the concept of DFT. Till time what we have studied was in terms of just one dimensional signals, and we were just looking on this mathematical interpretation. We were just imagining that it will be periodic. We were imagining that this will be the DFT. So now what we are going to do, we will implement the DFT first in our octave. Then we will see the various property of the DFT, then how translation takes place, what will be the impact of that in the frequency domain, translation and all those impacts. That property is the periodicity. We will see that periodicity occurs or not, that we can verify. So exactly whatever we have studied so far, that you are going to implement in octave or not, maybe on images we will do that, but majorly we will start with the vectors, and then we will go for the arrays, that is images. And so what is today's agenda? It is like to implement DFT, to implement various properties. Like we can see the periodicity, we can see the translation property that we have studied in the theory session. We will also see that center element of the DFT is high. We are seeing that if you want to see a DFT, we cannot see directly using unsigned integer 8, because we have to use what we can say, we have to use that log transform. So again we will apply that and we will see everything here. So that is our today's agenda. Then afterwards we will go to remaining topics of theory, so that we can cover in the next laboratory, we can cover more details of frequency domain. Okay, so today many of the concepts that you have studied in the theory, which you have imagined so far, will be cleared. Okay. So now, so that's why what we will need is, so we need the equation of DFT. So why I am going for DFT, not Fourier transform? The reason is I am using continuous signal f of t, right? Then in Fourier transform, I am using this continuous domain. Input is continuous, output is continuous, and that is not possible to have the continuous signals in my digital domain. I cannot have. I must have digital signals which are discrete in nature in my computer. Otherwise, it is not possible to store any continuous signal in the computer. So I cannot have input continuous, I cannot store output as a continuous one. So there is no meaning of discussing Fourier transform in the digital image processing, or rather in the processing where we are using computers. Okay. Um, so what we are going here is, we will start with DFT, and we know that what is the equation of DFT? It is equation, you have seen this proof and everything. This is my equation of DFT. Here my input signal is there, input samples are there, then e raised to minus j2 pi mn by capital M. Capital M is number of samples of input and output, right? And what we can say is, small m is for the sample number of output, and small n is sample number of the input. Both are in discrete samples, so we need m and n both as index for input and output and input respectively. So I think this equation you have studied, you know very well. And then we have this equation for the inverse Fourier transform, and we have taken one example as well. But now instead of taking the same example, better we take one more example. So two advantages we can have here. One will be the practice example. We will have the same example. If we are repeating, it is not making any sense. So better let us take one more example. So quick, what I need from you is that quick outputs F, capital F, M. Right? Suppose I say my small f is given by 1001. This is my small f. Can anyone tell me what is my capital M here? Can anyone tell me what is my capital M? What is capital M? Number of samples. How many samples I have here? Total number of samples are 4. Right? True. So the total number of samples are 4. Now, Okay, so my range of m and small n will be from 0 to 3, 0 to 3, right? So now what I want capital F0. Capital F0, that is my m value 0. I want capital F0. How to find out? So m value is 0, Fn e raised to minus j 2 pi m value is 0. So e raised to this term is going to be 0. So this term is going to reduce into summation of Fn. So what it will be? Can anyone tell me what will be my Fm? It will be just summation of yes, it will be just summation of Fn, and that will be 1 plus 0 plus 1. That is true. It is quite clear here. Same way now I am going for capital F1. So this is how we can practice our examples. We can have various examples. Capital F1, and what will be the value? So here you need to do calculation because my capital M is 4, my small m is 1, n can vary from 0 to 3, and just do the calculation. Take some, you can take time and you can give me the answers so that we can move ahead. So we are going to do implement this first in a octave. And just be tell me the answers here. Please tell me your outcome. Calculate and tell me your outcome. Okay, answer is 1 plus e raised to minus j 2 pi 3 by 4. What it will be? E raised to minus j 2 pi 3 by 4. Vidhi? E raised to minus j 2 pi. Actually, we can say it is e raised to minus j 3 pi by 2. So what it will be? E raised to j 3 pi by 2 results into cos 3 pi by 2 minus j sin 3 pi by 2 results into. Yes, it will result into j. And that's how you can see the results here. I hope you can see the results here. That is e raised to j 3 pi by 2, or we can say 270, whatever you consider. That will be considered result into plus j finally. So that's why your second component is going to be 1 plus j. And if you will continue with the same way, if you will continue, then you will get next two components 0 and 1 minus j. Next two components, because x2 and x3 we will find is 0 and 1 minus j. So I'm not we will not wait for the next two components. I think you are, if you can calculate one, other components are of course are clear. First component is quite easy, all summation of all samples is the first component. Next component onwards little calculation is required, and if you can calculate one, you can calculate others. Right? So if you want to check, so what we will do here, we will substitute n values 0, m value is always 1. You can check this is m value, this is m value is always 1, and we have substituted n value n0, n1, n2, n3, and if you will simplify this, if you will simplify this, this is going to be 1 e raised to 0. That's a 1 plus. This is also going. These two terms are these two terms are also 0 because my terms why they are 0, not because of exponential, but my sample itself x1 and x2 are 0. That's why these two terms are 0. And next term is like 1 plus. this term, right? 1 plus what you can say, this is what e raised to minus j 3 pi by 2. This is how it will result. And you know that this e raised to j 3 pi by 2 is going to result into j. That's why it is 1 plus j. Okay. So that's so finally what we have. So what you are going to remember? My answer is 2 comma 1 plus j 0 1 minus j. Now this I want to implement in my octave. It is not a difficult thing to implement. So let us implement that. So what I want is first I will start implementing. For that, what I need, one variable a vector is needed. Okay, so what I will do here, first I will have the basic commands. Now what I will do, I will have one vector which is having value 1, 0, 0, 1. Or other, if I don't want to use like a, I can use small f. So the same terminology can be maintained. How to obtain small n? Not small n, capital M. How to obtain capital M? What should be my command to write capital M? Okay, let's try that size of f. Let's see. I'm running it. Just I want to check that my DFT1 already my DFT1 is my file name. Okay. So you can see what is M is given by 1 4. Why 1 4? It is actually the size size of this F is 1 cross 4. Size of this is 1 cross 4. So what should be my code line, or what should be my another command if you can suggest? If not, then can you suggest modification here? Size is not useful because it is going to give me 1 cross 4. I want M is equal to 4 only. Any suggestion? Yes, what you can do, you can have a dummy variable f in which you can just, so that is of course a valid way to do. But one more command, I'm going to do that only. I'm going to do that only. But you can use the length. That is also fine. Size f second you can take. Second element of that you can take. And otherwise you have the command length as well. Length will give you the highest, what you can say, highest component or highest dimension. So that you can try. Length is also there, but I am trying with the W variable. That's all right. I may need somewhere, because see why it is useful to me. Why I am doing that, because ultimately I am going to do that for two-dimensional. So at that time, this is going to be useful to me. That's why I'm going with this. Otherwise, multiple options are available. Like you can change your function to length. You can just take second dimension from the size. That is fine. That you can take. But I am doing this, and the reason for doing this is so that I can use the same for the 2D, which is my image. I'm continuing this, and I will ignore S for now. So let me check whether it is working as per my requirement, and yes, it is working because it is 4 now, and it is S is 1 now. Fine. Now what next? What I have to do? I have to define capital F, but that's fine. It will. Okay, so now tell me what will be my next line of code. What I should write? So I will write first for I from how many elements I'm going to find. I need one loop for I. I mean I one loop for n, small n, and another loop for capital. Yes, one loop for small n and one loop for small m. So suppose I'm writing from 1 to m. That's fine. You can write from 1 to m. Right. I am just taking as many suggested. I am taking from to m. So, and then this is what is our assumption? This is working for, I is working for my m, small m. It is the sample for my output. It is sample number of my output. One more loop will be needed. I will not use j here. I will use k here because j I am going to use for complex numbers. E raised to minus j 2 pi term will need j. That's why I am not using j here. I'm going to use this as 1 2. What will be the range of k? K will also be 1 to M. The same thing, right? Now what should be the line? What should I write here? So what I need that for I should take my small f component. Which component? I should take small f of k. That is Fn. This is my Fn, right? Small f of k multiplied with exponential, or rather I should exp function you can use, or e raised to is suitable here. E raised to minus j 2 pi. What will be term here? E raised to minus j 2 pi. What should I write here? By capital M. What will come here? E raised to minus. So if you want, I can show you the equation as well. If you don't remember, this is the equation. So I took it in my case m is equal to I, right? So what should be, and this m is equal to k. Small m I have taken as k. What should be the term here? Can I write I into k? No. That's what my point was. You cannot write k into I. Why? Think. Okay. Yes, it should be k minus 1 into j minus 1. The reason is here, if you see your equation, yes, true. Rom's answer is correct here that m and n varies from 0 to m minus 1. So first value of m and n becomes 0. If I will start with I and k, it will never be 0. So what should I write here is, why I have taken 1. So you may say, okay, you can take 0 now, but if I will take 0, then index will be 0. That is not possible for my case. So if I am taking k here, what I have to take? K minus 1. I minus 1, k minus 1. Fine. So for every term, it is multiplied, but what I need to do, I have to sum up. For summing up, I can opt for capital F, or rather I can have here my capital F is equal to F of I is equal to capital F of I plus this. And when if I represent F of F is equal to zeros of size Sm. So all F terms are now 1 cross 4. F is now zeros of 1 cross 4. And this is, I think, is sufficient for summation. I think you can understand this. It is not difficult to understand, right? Observe, any doubt here? This is just for the summation purpose. You use some temporary variable, or you use this. You are used to this. Any doubt? So let us run it, and what answer we are getting here is, let us see what we obtain as capital F. We obtain as 2 plus 0i, that is 2, 1 plus 1i, that is 1 plus j, 0, and 1 minus j, and that is what was expected. That is what was expected. 1, 1 plus j, 0, 1 minus j. Okay. So this is the simple DFT equation. That's all right. So now we have DFT equation with us. Okay. So one dimension DFT, IDFT will be your task in assignment. So, assignment for exercise 7 and 8 will be combined, and I will give you 10 days time for that. Is we don't here we our focus is for the we will not have much exercises for this laboratory. I hope you have checked that your governance portal, and that already I have placed exercise 7 and 8. This experiment is not having more exercises because it is just fundamental understanding. Based on this understanding, we will have the next laboratory, And in that laboratory, we will have sufficient exercises, or rather, we should say, better exploration. We can explore better in that experiment. Here, just for basic understanding, one or two examples are given that you can check. Mostly, it is based on whatever we are doing for the DFT. The same thing we are going to do for the IDFT. That's it. Yes, it uses J and I both. You can use J and I both for the complex. But if I is defined as variable in image, then it will be taken as variable. If it is not defined as variable and if J is used, then it will be taken as complex. It is not for in the octave, but also in MATLAB. In both cases, it is the case, right? So this is it is very simple to define. Here, if you will see, it is used I. They have used I. I and J both are permitted. The same case is with the MATLAB as well. Okay. So now what we are doing here? So this is done for DFT one dimensional. IDFT is your task to do. How it is different? It is not anything much different. Just exponential will be positive, and here 1/m will come. Otherwise, it is as it is. So right now, many of you might have tried. Right? So that one task is over. Now I want extension of this to 2D. This is what I want to try. Okay, let us try this. Now it says use the same code. I'm taking this the same code I'm taking, and tell me the changes here. So what I want is two dimensional. So first of all requirement will be my function should be uh, 2D. So instead of using this, I'm using say 4 into 1 of 4. What do you understand by this? Once 4 means it is 4 cross 4 matrix of 1 multiplied with 4. That is all 4. That is 16 fours are there. Then what I need the size of that. So definitely it will be 4 and 4 zeros. So same size of zeros will be needed. So after this I think it will be as it is. Just tell me the changes here. How will you implement this? How many loops will be needed? Will 2 loops be sufficient? 3 loops or 4? U, V, both. And if you have optimum code, then I will not mind. You just give me the code. Otherwise, what I can see here is 4 loops. But if you can find out some optimum way to implement, I always go with your implementation. So now I will just wait. You just implement and tell me the code line by line, whatever you want to implement. It's 3 loops, 4 loops, 2 loops, even if you can do. Whatever your code is, you can show me. We will try whether it is correct or not, and then we can try. Because right now you don't have anything to verify na, whether your answers are correct or not. So now first tell me how many loops you concluded. Are you going to work with 3 or 4? For you and we want to need 2 other loops. Are you working with 4 loops now? Okay. So then it's good. So for the 4 loop, because one loop for x, another loop for y, and one loop for u, and the next loop for z. 4 loops are needed. So fine, you work and give me your code so that you can implement it. I don't think it is much difficult. I am giving the name as I1, K1. What will be the range of I1? So that I1 and K1 are nothing but U and V. Rather, I should use U and V for better understanding. I will use U and V now. I will write instead of I1, K1, I should use U and V. And I will need one more and so this is fine, I guess. Now just 2 changes in the code. Here it should be not I, it should be UV. 2 variables, this also should be UV. And this should be IK. It is XY. I can write this as XY as well, so it will be even better to understand. I'm taking it as X comma Y. Y. E raised to xy, e raised to minus, I mean, f of xy, e raised to minus a to pi, x minus 1, sorry, x minus 1 into x minus 1. This is the term that you are going to tell me what it will be. Here, x minus 1, u minus 1, x u, ux. But in both cases, I am going to use minus 1 term. The reason you know well. Plus divide by m plus here if the problem is s and m will come now. So here this will be s and here it will be. You can of course verify. You can tell me if I am doing anything wrong here. You can please tell me. So and see here it should be m. 2 dimensions mn. I am using it sm, so I have to use accordingly. What we did, this multiplication, this is it. Okay, so bracket is working fine. And bracket is lesser. Please verify this term if it is for I. If it is fine, let me know. It's visible then. And here it will be U will vary from 1 to S, V will vary from 1 to M, X will vary from 1 to S. That is one dimension, and second is other dimension. Let me know if anything is wrong here. F of uv plus f of x y into e raised to minus j 2 pi xu by s plus yv by m. Seems correct. If not, then we can definitely check later. Seems correct. Okay? Let us run it. And the result is capital F, capital F. What it says, it is 64, or rather we can see it here as well. It is not the, see here it is actually e raised to minus 15 is so nearby 0, so it is ignored here, right? So they are actually it is 0 only. That's why it is coming here 0. It is having some values after so many after 15 zeros, or rather I should say 14 zeros. So they are almost equivalent to 0. So what is my answer here? That 64 all zeros, all zeros, all zeros, all zeros. Right? So I am just getting 64 and all others are zeros. Okay, this is what we have obtained. What we have obtained 64 and all other zeros. Before we go anywhere, one interesting observation I can show you. All of you are comfortable? Should I repeat here or should I wait? Should I move ahead? Are you comfortable now? Should I wait? Are you doing? Are you implementing it? Okay. So now, what we are having here is now an interesting observation we wanted to see. Instead, what if I am having all ones here? What will be the result? Let us observe. The result is we can check what is the result. In my case, it will take time. But what is the result? The result is capital F. It is 4, 0, 0, and 0. Okay. So here I had 4. Let us plot. Let us draw that. Let us plot it. How it looks. Or I can plot it here as well. So it's not needed here also. Let us plot how it looks. So answer is 4, 0, 0, 0, all other zeros. When my input is 1, 1, 1, 1, right? How to plot this input? So input is 1, 1, 1, 1. This is discrete ones. Suppose I want to resemble it with the continuous, then how it will look like? If I want to resemble this with the continuous, that is 1, the next point is also 1, the next point is also 1, all the 1. So it will look like a constant line, 8, 1, right? All the points and then 1. So this is my input. See this, you observe this. This is my input. This is my input, and this is my output. On one observation. Okay. What was the next previous observation? that my input, if you can recall, my input was 1 4 into 4. That means it was like 4 4 4. How many fours? So we can say we were having 16 fours, but all were fours, right? All were fours. And that's why the answer was 64. The first component is always summation of all. And if you remember, if you total 16 times 4, that is 16 into 4 will be 64. So result was 64, 0, 0, 0, 0. If you remember, 64 and all other zeros. And what was the input? The input was 4, 4, 16 times 4s. And if you resemble it with the continuous, it will look like constant 4, right? So now what we have, if my spatial domain is a constant 1, I have a spike in frequency domain. True? If my input is constant, I have a spike in my frequency domain, then where my input is constant in 2 dimension, or it is in 1 dimension, I am going to get just one spike. If my input is constant in 2 dimension, I will get spike in 2 dimension, because if you remember, 64 zeros were there. Here, oh sorry, 16 zeros were there. Here also, or in this line also it was 0. Here also it was, they were 0. On both the axes they were 0. 64 rows and columns were 0. Why that happened? Because my input was constant in 2 dimension. That all four. This is the constant in 2 dimension. I got spike in 2 dimension. It was constant in 1 dimension. I got spike in 1 dimension, and the height of spike definitely depends on what is your constant value. And you can understand mathematically, if you want to understand, that this was zeroth component or the first component or corresponding to the component value, ij value 0 or mn value 0 or xy value 0, whatever you consider. So if, sorry, ub value 0, because here it was 0 0. So what we want is, it will be summation of all that we have just seen. Summation of all is nothing but 64 here. It was 4 here, 1 1 1 plus 1 plus 1, all 4. Now what is this? This is already you have proven in continuous domain. This is what you have proven in continuous domain. What is inverse Fourier transform of delta omega? What is inverse Fourier transform of delta omega? Let us find, instead of finding Fourier transform of this, I am finding the inverse Fourier transform of delta mu. What it will be? This already we have, but instead of using that, what will be inverse Fourier transform of delta mu? Substitute that delta mu here. What will be the result? What will be the result? What is f of 0? What is f in our case, Priyal? What is f of 0? Yes, it will be 1, because my function is this. This is my function, na? Delta mu multiplied this function integrated, so it is going to be 1. So what is my conclusion? That if my Fourier frequency domain is delta mu, my time domain will be 1. Let's plot both of them. Let's plot both of them. Time domain 1. How to plot time domain 1? For all the time it is constant 1. This is how it is plotted. What is output? Output is delta. Delta is centered at 0. So that is sudden spike. It is sudden spike in the center. Yes or no? And that is what we obtain. Our input was constant. Spike is in the frequency domain. And this is what we obtain. Because our input was constant, my output has to be impulse. If I will give impulse, na, suppose I am giving impulse as the input, that we can see. Now tell me, if I am giving impulse as the input, what I am expecting in the frequency domain? It is a constant value that I am expecting. Let us give that here. Instead of giving like this, I am giving like 1 0 0 0. What is my expectation? My expectation is that it should be giving me I have given impulse as input. Impulse is what? Certain at a certain location it is high, otherwise it is zero. So if it is impulse, my output should be constant. Let us see. And if you will check capital F, it's all one. Input was impulse, output is constant. I hope you can understand this now. And what that's why DFT is for discrete, but otherwise concept of the Fourier transform will remain same all the time. Okay, so what we have proven? We have proven this. We have understood this one. Okay. Now, some of you may say, okay, that's we understood that we are getting impulse, but I generally impulse is located in the center. Why your impulse is on the corner? What I expect if I give constant na, that there will be the immediate transform at the center, right? And the reason is because I am taking samples from 0 to m. My impulse exists here. That's why it is my first component. My result will be here, na? Actually, it is 0, 0, 0, 0, 0, 0, 0, 0. If I am taking this many samples, I am going to get this at center. But you know that we are taking sample from 0 to m. We are taking samples here. And that's why my impulse is located in the first position. So some of you may say, no, but we don't like, if you are taking 0 to m, that is our limitation. We cannot take samples beyond this. We cannot take sample before this rather. So what to do? What we can do? So that is also we have discussed that if this is the issue, what we have to do? We have to shift frequency domain. So what I have to do? This should be shifted. This location is shifted here. If this impulse is shifted here, I can show that. If this here is this impulse, I hope you can understand. That's why we are getting it in the first location. But if I don't want it, so what I can do, I can shift entire frequency domain by m by 2. So my impulse will be here. And then if I am taking from 0 to m, my sample is going to come in the center. And that is what already we have discussed in the last lecture itself. That because I am getting four corners, that is true for any of this one dimension or two dimension, anything, right? So that is what we have already discussed. Because I am getting from 0 to m, I am getting two end-to-end samples, or in two dimension, I am also getting four end-to-end samples. What to do? Shift it by m by 2 in one dimension, m by 2 and n by 2 in two dimension. It was quite simple. But to shift it frequency, I want to shift it in frequency domain. I want to shift it in frequency domain. To shift in frequency, what I need is translation. I need translation property. I need translation property. What it says that if you want to shift in frequency, then you have to multiply with some exponential in some. You have to multiply that with some exponential in time domain. Okay, so we will come to this point. We will do that. We will shift it. But these things you should know. These things you should realize. Okay. So now we will come to this point. But for now, where our actual discussion was on two dimensions. So for this, so it is expected. Why we went there? Because it is expected that it is going to be one impulse because my input was constant and it came as my expectation. So my code is working fine. But still, if you want to check whether it is fine or not, so what you can do is you can use FFT as your you can use FFT which is inbuilt command, right? And what you can give as input, in input you can give F, small f, which is my input, and I'm going to get answer as 111. That is FFT command is for finding DFT in one dimension. Inbuilt command. For two dimension, what is that command? For two dimension, I have to run this first because so that my workspace will be loaded. Okay. So now what I have f is equal. So my input is ff2 small f, and this is what my result is 640000. That is what I am also getting. Okay. So this is, of course, the implementation is quite sophisticated than our implementation because they have gone for all optimizations. Some of you may say, okay, this is for DFT in two dimension, DFT in one dimension. We have IDFT and sorry IFFT and IFFT, IFFT2 for inverse Fourier transform that you can check later. So some of you may say, okay, this is for FFT, but sorry, this is for DFT, but why they have given name FFT, not DFT? The reason is it is actually using fast Fourier transform algorithm for to find discrete Fourier transform. FFT is for the fast Fourier transform algorithm. They are not using this naive implementation. This is our naive implementation. No? Four loops we are using, and those who are doing the coding, there many of you are doing that, and you know that the number of loops we just want to avoid the number of loops, and of course otherwise you can also understand that in number of loops are more, then time complexity is going to be high. So this implementation is definitely good, not good. So we want some better algorithm FFT, but it is not our a requirement right now to learn that algorithm, but it is for finding DFT. Okay, so FFT fast Fourier transform, the name itself says, right? So FFT, so it is inbuilt function, but we will use this inbuilt function only now onwards. Why? Because it is so slow to use this DFT. If you want to check, if you want to realize it, here it is not that slow because our input is just 4 cross 4, but our image will not be 4 cross 4, right? So that for that I am modifying this code for our image, but I cannot take regular image dimension which is above 100. I will just take the dimension near to 50, 25, 50. I have tried with 50 and it is taking considerable time, but still you can realize that how slow this is. Logically, you can understand number of loops are more. So I'm taking one image, that image of lab 3. If you remember this image, that I am going to take, but size of that image is 512 cross 512. I have to resize it. Let us take that image, then resize. What was the command to load the package? Because I will use im resize. If I am using im resize, then it will not let me use without loading image package. So what is the command for loading that package? Image, what was that? First let me write im resize. And I am writing it as f1 so that it will be with me, but f1 is not required, f is needed. F is equal to im resize of f1, and size I am taking is 50 cross 50, so that I can understand how this DFT will be calculated for image. What was that command? Load, package load image. Okay, I am taking it. Thank you. It was needed. Okay, so package load image command is I think it should work. Okay, let us see. Okay, so what you need here is here complex numbers and multiplications will need double. So what I will do, I will make this not IM to double, I will use just double so the data type is changed. Earlier it was working well because I defined it once and once were already using, it was giving you double. So what is my point? What we will do now? What is our next target? I am doing this for image, and then we will see how my FFT of image looks like. Can I see it easily? If not, then do I need log transform? If I will use log transform, how my image will look like? How to find its magnitude of image and phase of the image, that we need the magnitude and phase. So next our target is to learn that. So which portion we are learning right now? Of course, it is going to take time. It will take time. So we should. So then till time we can find out something else as well. So what we are doing here. So I think you understood this 2D discrete transform now, and now we are working for translation properties and all those things we are going to learn now. So what we can do, we can write the code for translation property, so that when this will get completed, we will learn it, and then quickly we can run that code of translation property. Let's do this, right? For what? I will do this for the same code. I'm using the same code here. Let's do translation property. What I want is that 64 was coming the corner. I will not use this image because it is going to be too heavy for to use every time. 4 into 1 of 4. That is my standard one. That standard constant one. Okay. And what I want is, I don't want to find. I want to so my what I'm getting as answer 64 and all other zeros. But what I want, that my 64 should come in the center, right? So that's why I need shift by m by 2 and n by 2. You know that it should come in the center. I want to shift that 64 in the center by from the both direction. That's why instead of at 0 0, it should be at m by 2 and n by 2. So that's this why I have to keep this m by 2 here and n by 2 here as u0 and v0, right? So here m by 2, here n by 2. So m and m will get cancelled. 2 and 2 will get cancelled here. That 2, I think simplification, we have studied this, no? We have studied this. So simplification of that will result into what? If I want to shift, then if I want to shift, then what I have to do? This. This m by 2, will get cancelled, nn will get cancelled, and 2 is common both, and that will get cancelled here. It will be raised to j pi x plus y, and we concluded that it is going to be minus 1 raised to x plus y. So what I have to do? For my input, I have to multiply it with minus 1 raised to x plus y. My x varies from 0 to uh, m minus 1, y varies from 0 to n minus 1. So instead of finding Fourier transform of f, your now f should be, or f should be altered with f into, here what I will need, I will also need again two loops. Or if you can find better implementation, I will always appreciate. But what I right now I can think is, I need for f of xy, I don't want f of xy as it is, but I need f of xy into minus 1 raised to what? X minus 1 plus y minus 1, which is xy, but x and y. But again, if you are keeping it x1, then also it will not be problematic. But anyway, this is, I think, you everyone can understand. See, still it is running. 4 loops are there, so it will take time. Okay, so what we have now? What I did, I took my input, I multiplied it with this f of xy with minus 1 is to x plus y. So why I did it? If I will do so, actually, if I am multiplying this, that means I am multiplying. If I am multiplying this, that means I am multiplying this. And why? What is the significance of this? If I am multiplying this, that means I am shift e exponential by. What is my m? What is my question? How much we will get here? Yes, it will be 2. So actually, I will get shift by 2. Earlier, it was at the location here, shift by 2, and it will get shift by 2 here as well. So it will come here. So it will be at the location 3, 3. This is one location, na? Shift by this. And by 2. Okay. See here, what is our assumption? Our m by 2 and n by 2 is always integer only. Consider the reason it's most of the time, right? All make it even. The reason will come. So here is the issue that is what if that I will not be the case ever. Did I get output? Yes, output is possibly if any reason comes, I have to again get. So DFP. Now what I want, so my image was 50 cross 50 because I resized. So let us see first image. We are going to get it. Okay, it is already out. The reason is it is in double, na? That's why it was showing white. And it is expected, right? It was expected. So with this, how my frequency. So now let us see, read the value and zero component. It will max function, max of max, works with capital F. Yes, it is working. 2,68,966. Zero component or zero component is the maximum component. This is ML F bar. This is what F bar of XY means average intensity of what? The skate image. Let me show you. This image now it's more clear now. And this is called as DC component. 00 other components are also very high. 2,000 values are there. We use the left will it work? First of all, it is a complex number, so